Hi everyone. In this video, I'll talk about Euler's circuit and path theorems. So these are theorems that give us a complete way of understanding whether or not a graph has an Euler path or has an Euler circuit. And you'll be surprised to find out that it's not too difficult to see whether or not a given graph has such a structure. So before we jump in and write down these theorems, I want to remind ourselves about the degree of a vertex and then give a little bit more vocabulary, not much, to vertices and their degrees. So recall that the degree of a vertex in a graph is just the number of edges connected to that vertex. Number of edges adjacent, number of edges adjacent to the vertex, to that vertex. Now, if it is the case that the degree of a vertex is odd, we just say that the vertex is odd. And similarly, if it's even. So if the degree of some vertex V is odd, or parenthetically even, say respectively, even, we say V is odd or respectively even. So that's just some language that we want to have to state these theorems. All right, now let's just jump in and we'll write down the circuit theorem, and then we'll write down the path theorem. So here's the theorem for circuits, Euler's circuit theorem. What does this say? Okay, so, well, it says if a graph is connected, remember that means I can connect any two vertices by some kind of path, and every vertex is even, has even degree, then there is an Euler circuit. On the other hand, if a connected graph, well, certainly if it's disconnected, so let's say it this way. If a graph is disconnected or has at least one odd vertex, so not all of them are even, then there is no Euler circuit. Not Euler circuit. So this gives us a complete answer to the question of whether or not there's an Euler circuit. We just have to check the degrees of all of the vertices. So let's do a couple. I'll just draw some examples. So let's say we have, and I'm going to just draw little dots for my vertices to make things simple. So if I have a graph that looks like a bow tie, say this, then there should be an Euler circuit here. And the reason is we can look at the degree of each vertex. This has degree 2, this has degree 2, this has degree 4, 2, and 2, right? Um, and all of those numbers are even, so we would say all of the vertices are even. And indeed, we can easily find an Euler path, an Euler circuit, pardon me, by just starting at 4, say, going around in a loop, and then going around in another loop. And this is tracing out an Euler circuit. Just following the arrows, starting at 4. And so, on the other hand, if we had the same exact graph, let's duplicate it, and we all of a sudden removed one of the edges, we've changed the degrees of these two vertices, right? And as such, we now have a degree 1 and a degree 3. And now we don't have any Euler circuit. There's no Euler circuit whatsoever. And yeah, this is what Euler's theorem says. Of course, if you disconnect the graph, there's no path at all from one vertex in one part of the graph that's disconnected from the other. So if it's disconnected, there's no dice there. Okay, so let me just say why. I want to say a little bit about why this part of the theorem is true. If a graph is disconnected, it's pretty clear that you can't connect all of the vertices through an Euler path. Well, I guess disconnected and assuming that the graph is not, there's not an isolated vertex in one of the parts of the graph. Okay, so let's just avoid that particular case. So let's assume that there is an Euler. Let's see why this is true by thinking about our graph and assuming that there is an Euler circuit. Okay, so suppose I'm going to make an argument that will explain why this part is true. So let's suppose, oops, suppose that the graph is connected. And suppose for the moment that that there is an Euler circuit. Okay. Well, let's take any vertex. So take a vertex, which is not, oops, which is not at the beginning and end of this circuit, which is not a starting, which is also, so since it's a circuit, it ends where it starts, so it's not a starting or ending vertex. And let's draw a cartoon of that, a little illustration. So I have some vertex here, and I have a bunch of edges. And I don't know where they're going or what's going on with these edges, but I've got a bunch of edges. And now I know this is not in the beginning or the end of my circuit, but I know that some person or whatever we're imagining is tracing out the circuit. And since that circuit has to hit every single edge, there at some point someone going along that circuit will cross into this vertex. But when it crosses in, since it's not the ending vertex either, it has to also leave. So in other words, when that person taking that Euler circuit passes through that vertex, it takes in one edge and then it leaves on another edge. And so that is two edges that it just went through. But it has to, hit every single edge. So it gets plus two edges when it crosses through once, and then when it goes again, it gets another plus two edges. And then when it goes again, it has another plus two edges. And when it crosses through again, it has another plus two edges. So however many times it's actually crossing through that vertex, it's adding two edges each time, which means that the total number of edges, if there is an Euler circuit, connected to that vertex is even. It's even. So that's why now that tells us that the degree of that vertex must be even, or that that vertex must be an even vertex. So this argument of passing through that vertex is telling us that the vertex must be even. So what am I saying? Since every path in or edge time, the path goes into the vertex, it must leave that vertex, must leave along another edge, another adjacent edge, adjacent edge. We see that the degree of that vertex is even, which means that the vertex is even. So that's what happens if it's not the beginning or the end. However, if it is the beginning, then yes, the first edge out you'll leave, which means you decrease the number of edges adjacent to that beginning vertex by one. So let's say we are now in a different situation. We're starting, this is our start vertex, and we have a bunch of edges connected. And we leave. We start our path and we leave and we go and we do a bunch of other things. And well, it's an Euler circuit that we're on. So it must come back. I mean, it must hit each of the edges adjacent to our starting vertex. But if that's not the last edge, then it must leave again and hit more. So then it has plus two. So when we first leave, we're hitting one of the edges connected to our starting point. But then when we pass through again, just like we did before, we have to add two. And the difference with with an Euler circuit is that the starting point is also the ending point. So this is also the ending point, which means after we're all done with the path, the last edge in that path must be coming in and adding one more edge. So in this case, we get the leaving edge, which is one, a bunch of pass-through cases, which is 2 plus 2 plus 2, however many times, so it's some even number, and then the last edge, which is another one. So we have an even number, we have 1 plus an even number plus 1. But that's 2 plus an even number, which is even. So the starting vertex has also an even degree. So this verbal argument says the starting vertex, starting equaling ending vertex, also has even degree. Means that it's even, i.e. it's even. So it is even. And so what does that tell us? That tells us that if it had one odd vertex, then it could not have had an Euler circuit. What it doesn't tell us is this first claim. So this first claim is saying something a little different. It's saying if all of the vertices are even and it's connected, then you can find an Euler circuit. Then there exists one. See, this whole argument I just made, I assumed that there was no Euler circuit. So this theorem's a bit stronger than that. It's saying, well, in fact, if you're in the case where they're all even, you actually get an even one. Okay. So let's apply this circuit theorem to one of our problems. If you recall, we had this bridges of Königsberg problem, and we turned that bridges of Königsberg problem into a graph. And I'll just reproduce that graph right now. We had sort of, we had several bridges, and oops, I had labeled these land masses. It was like I'm going to get the labeling a little bit different this time, so I hope you'll excuse me. But there were four land masses, and then we drew bridges between them, and we made those bridges. Well, we had those bridges turned into edges, and we got a graph like this. And this is the bridges. B would be the island in this case. So the bridges of Königsberg problem is precisely this graph up to some relabeling of the vertices. Okay. And so so I missed an N there. Oops. So now we can ask, is it possible that there is an Euler circuit here? And the answer is no, because we can write down the degrees of all of our vertices. So if we do that, we just count up how many vertices or how many edges are connected, say, to D. 1, 2, 3. So the degree there is 3. And already we know there's no Euler circuit already because we've got an odd vertex. It's a connected graph with an odd vertex. We're out of luck. But let's continue and let's write down all of the degrees. We get a degree 3 for A, we get a degree 5 for B, and a degree 3 for C. And this tells us that it's very much not possible to get an Euler circuit. So you might ask, though, can we get an Euler path? I mean, can we at least get some kind of route where if maybe we don't end where we start, but where we can just traverse each bridge once. And for that, there's Euler's, well, sorry, there's another theorem, which is Euler's path theorem. Okay, what does it say? It says if a graph is connected and has exactly two odd vertices, then there is an Euler path between those vertices. So in particular, Euler path starting at one of the odd vertices and ending at the other. Okay. Vertex and ending at the other. Okay. On the other hand, if a graph has more than two odd vertices, a graph has more than two odd vertices, there are no Euler paths. So what is that saying? Well, if we look at our bridges of Königsberg problem, it's hopeless. It's hopeless. We have all of the vertices as our odd vertices. certainly more than 2. So there is no Euler circuit by the Euler circuit theorem, and there's no Euler path by this theorem here. So sadly, there is no such path in this case. However, if we look at the earlier example that was drawn up here, where I deleted exactly one of those edges, we can see in this case, we do have 2 vertices that are odd. And indeed, there is an Euler path. And in fact, it's sort of the one that is drawn here, or at least in one direction. If I start at this vertex, I can follow the arrows and get an Euler path that ends at the other odd vertex. So Euler paths certainly do exist when you have this property that two of the vertices are odd. The justification for the Euler path theorem is very similar to the one, or at least the part of the Euler path theorem. This part here is similar to the one I went through for the Euler circuit theorem. It's just the idea, if we have an Euler path, and we're not at the beginning or end of that Euler path, we have to pass through that vertex an even number of times. And in other words, we have to go in and out of that non-start end vertex each time we cross it. And because we have an in and out, we have 2. Each time we cross, we get 2 edges connected. And since none of them overlap, because it's an Euler path, we have an even number of edges connected to any given vertex. And then you make the similar kind of argument for the start and the end to say, well, since I'm not coming back to it, or because I'm not starting at it, or I'm finishing at it, then I have an odd number of edges incident or adjacent to that particular vertex, the start and the end vertex. Okay, so this is Euler's path theorem. This is Euler's circuit theorem. Next time, what we're going to do is we're going to take a look and see how we could produce one of these paths if we're in this situation. And we won't give some very rigorous mathematical proof, but we'll make some reasoned arguments as to why this algorithm, which is called Fleury's algorithm, actually produces these Euler paths for us in that case. All right.